So let's maybe, okay, today we will see a couple of two different theorems, which are different way of making approximations, or they are even called limit theorems about the binomial distribution. These are very important results, not the most general ones, but these are very important since the one that I think we will prove. And maybe I think that in the next lectures they will be generalized to more general theorems, but please pay attention because I think that they are very important results. So maybe we can start with a very quick recap about the binomial distribution, just to be sure that we're on the same page. Whatever. Okay. So how does this distribution arise? Now suppose you have an event which might happen or not. Like you have a fair coin, you toss it, and the event is, I don't know, that you get head. Okay, this event may occur with some probability. In this case, the probability is 1/2, is the coin is fair. And the probability that the event does not happen, so you usually have P, which in this particular case is 1/2. And the probability that the event does not happen is 1 minus P, which we'll call Q, and it's also 1/2 in this case, right? Okay, so you associate this random variable, for example, x, and this random variable will be 1 if the event happens, of course, and 0 otherwise. So you can rephrase the thing saying that the probability that x is equal to 1 is P, okay, which is 1/2 in this particular case, and then the probability that x is equal to 0 is Q, which is again 1/2 in this case, right? We can easily generalize, for example, think at rolling a dice, and then the event is getting, I don't know, the phase 2, and then P will be 1/6, and the probability that the event doesn't occur is the complementary, so 1 minus 1/6, which is 5/6. Okay? Okay, now suppose to repeat this experiment, like rolling a dice or tossing a coin, many times, say n times, and you associate different random variables to each repetition of the experiment, so x1 for the first repetition, and then you have x2, and then you have xn. Okay? So this is the probability that this is 1, again, is P, and that this is 0 is Q, and this is true for all these random variables, right? Okay, so now the question is, which is the probability that the sum of these variables is equal to k, a certain number. So this is exactly the probability of having k successes out of n different trials, right? Because it just can be 1 or 0. So if this is 1, it means you're having a success, then you sum it, you have k successes at the end, right? So the question is, any question? Okay, no. So you can call this variable Sn, because you're making n different trials. And the question is, which is the probability that Sn will be equal to k, right? No, k. Exactly k. These variables can be 1 or 0. You sum them. So k is an integer number, goes from 0 to n. You can have 0 successes up to n successes, okay? And so the answer is the binomial distribution. This is n over k, p to the k, q to the n minus k. Okay? this is the binomial distribution, and I don't know how you have called it. This is binomial distributions with parameter n p evaluated in k. Okay, so this is a discrete probability distribution. You can try to picture it like the variable is k. Then you need to fix n and p. So okay, you have just only integer values, 0, 1, up to n. Okay, and then you will have some shape, something which is bell-shaped, just to give you a flavor. Like you may try to connect this dot with just the contour, but the distribution is a discrete distribution, so it has only values on integer numbers. K can be 0, 1, 2, 3, up to n. Right? Okay. So now, if you want to know which is the probability of having k successes out of n trials, so for example, having k times head when you toss the coin n times, this is the answer. You just go here and replace the numbers. So for the coin, p is 1/2, q is again 1/2, n is maybe 10 times. And then you want to know which is the probability of having 5 successes. K is 5. Put the numbers inside and you get the probability. Okay? So this is just a quick recap. I don't know if you have introduced the binomial distribution in a different way, but you can think at it in these terms. Maybe you've used different symbols, but we're going to use the symbols during the lecture, so just to try not to be surprised. Okay. Okay, so I hope it's clear so far. And, okay. Can I just... Okay, so the first theorem we're going to see, it's called the Moivre-Laplace theorem, or sometimes I think it's called the local theorem. And so let me start again. So we're interested in the probability that Sn is equal to k, and okay, this is nk, p, k, q, n minus k. Right? So basically now we are going to make some approximations, and we will end up with a different expression. And okay, then we will discuss a little bit the limits of these approximations and some possible applications of this result. So just for the moment, try to follow me on the calculations. So okay, the first thing that you should know is this formula, which is called the Stilling approximation, as a way of approximating the factorials. So okay, this is true when n goes to infinity. Okay, so now we're going to plug this formula in this expression, which I will write down explicitly. Okay, so just we'll use it for n factorial, k factorial, and n minus k factorial. So we will get okay, we just used the Stirling approximation, which is true as far as n is a large number. Okay, this is already telling you that these results will hold for n large enough. Okay, this approximation will hold for n large enough. It makes some simplifications. You see that this one just cancels out, and also these ones. So we end up with square root of n. Okay, I'm trying to go very slow. If you think that some passages are obvious, just tell me, and I will be quicker. Okay. The derivation. It's a bit long, but it's pretty straightforward. It's mostly algebra, so okay. So now we're going to rewrite this way, P over K. Okay, I'm just, please. I'm sorry, can you speak louder? Here? Okay, why? Okay, yes. 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 Yes, okay, I think it will become clear in a moment when we'll discuss better the limits of this approximation, okay? So, yes. Okay, for the moment, just be patient and, okay? Just accept it and we will discuss the limits of the approximation in a moment. Okay, so I'm going to rewrite it. Okay, just write this as n to the k times n to the n minus k, and you will easily have p over k to the k, and then Okay. Just one very last step. You can then write this fraction as 1 over pi n k over n minus k n, and then it's okay. I also want to point out that this is not the most rigorous derivation that you will find of this theorem. If you're interested in a more rigorous one, then I will give you references, but just to give you a flavor of the proof, just to convince you that this result may hold. But okay, I admit that maybe rough edges in this proof, we will see it in a moment, but it's just to give a very intuitive proof of what this theorem is. Okay? There are, of course, more rigorous ways of proving it. Okay, so now couple of more passages, I think. Oh, no, not yet. Okay, so I will okay, so now let me introduce this variable, it's x. Okay. Okay, sometimes later I will call this xk because it does depend on k. Okay, but just for simplicity during the proof of the theorem, I will just call it x. Okay, so it's the same thing. So now you can derive k, which is mp x mp q, and you can also derive n minus k, which is okay. Oh, now one important thing that I want to remark is that now note that the probability that Sn is equal to k, okay, is exactly equal to the probability that Sn minus mp divided by mpq is equal to xk. Okay? Is this clear? No, because we're asking the probability that Sn is equal to k, so just look at this formula. The probability must be the same, right? Just replace k with Sn if you want, and then get the result, right? The probability that Sn is equal to k is exactly equal to the probability that Sn minus mp divided by it's equal to xk. Now, this variable, this is a random variable, because here you have a random variable, you are subtracting a number, then you're normalizing it, is again a random variable. It's what we will call a standardized random variable. Why? Because it has 0 mean. Is this the symbol that you're using for the mean? Yes. And then if you do the calculate the variance, it's 1. Why is this? Because if you remember, for the binomial distribution, you have that. Okay, no, that's not. I'm sorry, that's not. No. This is okay. If you remember the binomial distribution, this is NP. This is square root of n PQ. And then, okay, if you calculate the mean of this quantity, it will be 0. And if you calculate the variance of this quantity, it will be 1. So what I wanted to say is just this thing. This is 0. And then if you do the variance, okay, is this clear? Because you see, you have a random variable, which is this mean, then you're subtracting the mean, you get 0. Okay, divide by this quantity again, you get 0. And what about the variance? Okay, you do the calculation, and we'll get 1. So this is a standardized variable, which simply means that it has 0 mean and variance equal to 1. Okay? I think that in the next lectures we will see other limit theorems, and they all deal with standardized variables. Okay, this was just a brief detour. You can now, from this equation, calculate k over np, n minus k over nq. Okay. So just re-expressing that, rephrasing that expression in terms of this new variable which we have introduced, x. Okay. Okay. And can I delete this part? No? Not yet. Am I going too fast? No? It's okay? Too slow? No. This is the variance. Okay, I don't know how I view. It's just the variance of a random variable. It's just okay. I'm not sure that you've used the same notation, but it's also a good thing that you see different notations so you can focus on the actual ideas and concepts behind the notation. Okay. Okay, so now can I? Okay, one least manipulation. Let me rewrite that expression this way. Okay, and here you will have the logarithm of this expression, right? Then you use the properties of logarithm and you get E2 minus k logarithm of what? Plus x. Okay. You have minus and minus k logarithm. Okay, this factors remains the same. Okay. Okay. Okay, so for up to now, I think it's pretty straightforward in the sense that there are just algebraic manipulations. Now we are going to make some approximations. Just let me remember you that x is equal to k minus np divided by square root of npq. And now we will require that this number is a small quantity. Let me say much less than 1, so that we can use the series expansions for the logarithm. Okay? So this means that this result will hold true if x is a small quantity, right? So if k minus np divided by, it's a quantity which is small if compared to 1. Okay? What does this mean? Now, just remember for the moment how the binomial distribution looks like. Okay? Here we have k. And okay, this is not a continuous curve. There are just dots because it's a discrete distribution. I'm just drawing the envelope. And then you know that you have here the mean, which is np. It does mean that k minus np, right? Okay, so now we're requesting that this quantity should be much less than 1. So, which means that k minus np, okay, which is equal to x times np q. It means that this quantity can be larger than, I mean, the typical distance can be larger than, let me say, square root of npq, right? Because x essentially is of order 1, because you see it's a random variable, which is 0 mean and variance 1. So this means that this approximation realistically will be true near the mean of the distribution, but I mean, which is the meaning of near. Okay, essentially, it cannot be true out of this interval, an interval which is large, basically the standard deviation, if you will, okay, the square root of variance of the binomial distribution. Okay, this is just for giving you an idea, a very rough idea, because this is not completely rigorous, as I told you, of how good this approximation can be. Okay. Okay. Okay, so the message is just that we will replace, we will consider x as a small quantity, and we will use the expansions for the logarithm of this expression. I just want to remind you that the logarithm of 1 plus y, we can expand it and get y minus. Okay, and then you have other terms of order y to the third, to the fourth, but we're going to neglect it, right? It's just stopping to the second order, the expansion to the second order, because, okay, this quantity is small, as I told you, okay? Then you have other terms. Oh no, I'm sorry, it's not. Okay. So okay, I think that this is pretty clear. Yeah. Okay, so now we're using these expressions here and here. So the logarithm of 1 plus x q and p is, okay, if you develop, is okay, and I'm doing the same thing for 1 minus x p and q. You will get okay. Now, one more thing, remember, okay, this expression, if you, okay, this means that k is equal to np plus x times npq, and k divided by n is essentially p plus x square root of pq divided by the square root of n. Okay? So if you do the limit of large n, right? Remember that x essentially is a quantity of order 1 because it is 0 mean and the variance is 1. So it's not growing with n. Okay? So now if you do the large n limit, what you get is just p. Okay? Okay, if you want, this is in a sense the law of large numbers. I don't know if you have already seen it, but just telling you that you can rephrase it in this way. K is going to np, right? Meaning that you're converging to the mean of the distribution when n is large. Okay, so if you do, it's like, okay, you toss the coin a large number of times. How many successes, so how many heads do you expect to get at the end? The number of trials divided by 2. So exactly the number of trials and divided by 2 probability is 1 of. This is the number of successes, right? Just telling you that at the end you will converge to the mean of the distribution, okay? But you can see it very, straightforwardly from this formula. So we're also going to replace k over n with p, because in the limit this holds true. Okay, so basically these ones are the approximations. I just expanded the logarithm because we're saying that, okay, x, the approximation will be true when x is small, and for large n, k over n is equal to p. So now it's just a matter of doing some more algebraic passages. Can I cancel? Okay. Okay, so this is 1 over 2 pi n p, and then you have 1 minus p, which is equal to q. Times e2 minus k, and you replace this with x square root of q divided by times np minus x square q to np. There, n minus k minus x and q. Okay, we're almost there. Now it's just actually a matter of doing some algebra. Before that, you will want to replace k and n minus k with their expression in terms of x. Just going to, okay, maybe I've written it already 10 times, but it's worth remembering. npq and n minus k, it's nq minus. So now you're going to replace k and n minus k with that thing. So it's 2. I'm just writing down the argument of the exponential, okay? Here, just this part. Which is minus np times x npq. We have x, q, np minus x squared np minus what? nq times okay. So now if you actually make all the products and then simplify the terms. And okay, one important thing, you need to neglect terms which are of order 3. Like if you see now, if you do the product, you will get a term with x, a term with x squared, a term with x squared, and the term with x cubed. Now we're going to neglect it, right? Because we've expanded the logarithm. I've just stopped to the second order. So when you get terms of x cubed, you just neglected them, and that's also true here. You get x, x squared, and x cubed, and you neglect it. Now, okay, if you do the calculation, you should get minus p plus q. Very simple. Okay. Okay, this is a very simple exercise, so it's nothing special, just algebra. And since, as you remember, p plus q is equal to 1, simply get minus x squared off. Okay, is it clear? It's just a matter of doing very simple. Yes.
So this part here includes also the
No, it's just the argument of the exponential, right? It's just this part. Okay. Just avoid it to write it down. Okay, but then you have this factor e to this argument. I'm going to rewrite now. Just need to work out some basic algebra and you'll get this result. So at the end, you get what? Times okay, and then if you remember the expression of x in terms of m, p, q, and everything, you get here n to the minus k minus m p squared to m p q, and then again, I usually write it like this. Okay. Okay, so we're done with the first theorem. I just want to remember the other side of the equality, which is still this one. So the probability that Sn is equal to k is approximately equal to this expression. What this hold true? I told you can think at k minus mp, say mpq, okay? Maybe much less, maybe, okay, I'm not being very rigorous about this, about the limits, but just to give you flavor. It's just, this is called the local theorem because you're approximating the probability of getting Sn exactly equal to k, okay, with that number. You know k, you know n, you know p, you know q, plug in the numbers, okay, and get a value. Okay. And this is the local theorem. I'm going to make some more comments about it and see if I can very loosely convince you that you can write this theorem in some other way. There's another formulation which is called the integral theorem, and I'm going just to make something. Okay, but just let me know. Is that clear up to now? Okay. Very brief recap. I've not been completely rigorous, but the probability that Sn is equal to k, so it's essentially the number of successes, right? That's k, can be approximated by this expression, right? Which is also, as I told you before, the probability is exactly equal to the probability that Sn minus Mp divided by Mpq is equal to xk, right? If you want, you can put a k up here. Okay, I just decided not to simplify notation during the proof, but this is exactly the same thing. Okay, I hope it's clear, right? Okay. Can I cancel it out? So anymore. So now, just to be sure we do not forget this, okay, which is also the probability that, okay, Sn minus Mp equal to xk. Okay, and usually you write it down like this. Okay, it's the same thing. They're just the same thing written down using different symbols. Okay, so I told you before that xk is equal to k minus mp divided by mpq, right? And as you remember, for the binomial distribution, k goes from 0 to n, right? For the binomial distribution, k, just go, it's an integer number. They're asking about the number of the probability of having k successes when you do n trials. So k cannot be larger than n, of course it must be 0, the lower limit, okay? Because it's an integer number, you cannot have -1 successes, it doesn't have any meaning. Okay, so if you calculate now the end point of the distribution, so just replace k with 0, right? Okay, so what you get minus mp and pq. So this is minus okay. Now if you calculate xn, okay, this is very simple. This is just the end point of the distribution. So this is the x which corresponds to k equal to 0. This is the x which corresponds to k equal to n. Okay, and then you see that if n is large, This one goes to minus infinity, and this goes to plus infinity. Right? So for x, you have that the end point approach plus infinity and minus infinity. And then if you calculate x k plus 1 minus xk, which is simply the distance between two consecutive xk, okay, we'll call it this delta x. What do you get? Okay, I think this is very simple. You can check. It's MPQ. Right? Just plug in k plus 1 and then k and then subtract them, and you get this result. Is this clear? Okay. So as you see, this does not depend on k. And when n approaches infinity, this goes to 0. Meaning that this xk become increasingly close. Right? So it's like you're doing a continuum limit. When the n goes to infinity, the x go from minus infinity to plus infinity, and they're essentially continuum. Right? So you're continuously covering the real axis. Okay? Now, if you use this result, you can now rewrite this expression in a very simple way, like delta x times 1 over 2 pi minus xk squared of just isolated 1 over square root of MPQ, used this expression. And now you should recognize the Gaussian distribution, I think, with 0 mean and variance equal to 1, right? It's just the probability density function of the Gaussian with 0 mean and variance equal to 1 is exactly this one. Am I right? Have you seen the Gaussian distribution, right? Okay. So if you put mu, I don't know if you call the parameters equal to 0 and then sigma equal to 1, you get exactly this one. So this is that this probability is proportional to the probability density function, proportional by this term, to the probability density function of a Gaussian distribution. So what does this mean? Now, let's try to. Now I'm picturing x. This is 0. So this is, okay, more or less the probability density function of a Gaussian distribution. Now you want to approximate the probability that Sn is equal to k. So you have k. You plug in k here, and you calculate xk. Okay, so let's say xk is here. Okay. So you see that this value is exactly the value of the Gaussian distribution evaluated in xk. And then you are multiplying it by delta x. So, okay, now suppose that n it's large but still finite. This delta x it's still finite, so will be like this. This is delta x, right? I don't know if you can see it. So when you do delta x times this value, essentially you're evaluating this area, right? The area of this little. Okay. Is this right? Okay. Now, can I delete this part? Now let's move to this integral theorem. Now we're asking a slightly different question. So we're not asking the probability that Sn is equal to k, or equivalently Sn minus Np divided by blah 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 is equal to xk, but the probability that this quantity is in this interval. Okay? Now, note that in the large n limit, you can choose a, b, two real numbers. The only important thing is that, of course, right, a is smaller than b, but you can choose whatever numbers you want, because, as we saw, the large n limit means that x goes from minus infinity to plus infinity in a continuous way, right? So a and b can be simply now real numbers. They do not need to be integer or close to integers, just real numbers. So, for example, you have A, it's here, and B, it's here. Okay? So, how would you, okay, again, this is not rigorous, it's just to give you a flavor. I think it's the simplest way of getting an idea and convincing you about this integral theorem. So, again, it's not rigorous, but I think it will be pretty much convincing, because how can you write this probability? Okay, you just sum over all the xk which are in this interval. So for the moment, think that n it's large but still finite. So we'll have, okay, different values of xk which are in this interval. So it's large, so maybe xk will not be exactly equal to a, not exactly equal to b, but you can, in the large n limit, you can make them approach a and b as close as you want, okay? So how would you approximate that one? You just make the sum over all the xk such that, over all the k, I'm sorry, such that a xk b. You sum over all this contribution, which are a finite number for the moment, since n it's large but still finite, of what? Of the probability that Sn is equal to k, right? Or Sn minus Np divided, it's equal to xk. Okay? Which is simply, if you now replace this probability with this expression with maybe delta x, it's delta x okay. I've just used this one. Okay. Essentially, what does this mean? Just look at it. You're going, I don't know, let's start from here. Okay, maybe A, it's a little bit. This is the first xk over which you're summing. Then you're evaluating the number, doing times xk, and then you go to the next one, and then to the next one, to the next one, to the next one, next one, next one, next one, right? So you're calculating this area. this formula is the formula for this area with n finite, right? So just summing over all these different rectangles, because it's the value of the normal distribution in this point times delta x, right, plus the value of xk in this point of the normal evaluating in this xk multiplied by delta x plus, and okay, and then you go on. Right? Is this point clear? It's maybe subtle, but it's clear that it's just the formula of this area for finite n. Now, if you make n, if you let n approach to infinity, this approximation will be better, and at the end, you will get exactly the area of the Gaussian core, I mean, starting from A to B. In fact, this is exactly the definition of the integral, of the Riemann integral, right? Just calculating the area of these rectangles, sum them up, and then if you let n go to infinity, you get exactly the definition of the Riemann integral. So this is the integral from A to B of the x of 8 minus x squared of 2 pi. Okay. Of course, when n approaches to infinity. Again, this is not rigorous, but I think it's very intuitive. The local theorem is just telling you that you can locally approximate this value with the area of a rectangle, okay, for finite n. Then the integral term is simply telling you, okay, now you're interested not at the probability just in a point, but over one interval. What you do, just sum the areas of these rectangles and then let n go to infinity, and basically you get the integral, right? So basically this is the integral theorem. The probability of this standardized variable, the probability to be between A and B, it's equal to the integral of the Gaussian, between A and B, of the Gaussian with mean 0 and variance equal to 1. Okay. Now, the thing is that evaluating this quantity, sometimes it's much easier than evaluating this quantity summing over all the values of k. Because you see here you have to sum over many values of k. Now it depends from the numbers, but they can be even 1,000. I just need to evaluate an integral. And this integral, I mean, it's you can evaluate it numerically very easily. So this is basically the error. It's related to the error function. I don't know if have you seen the error function? You know the error function? Okay. So this is now depends on how you define it, but I think the best way of saying it is this is just one of the error function in B divided square root of 2 minus the error function in A divided square root of 2. So, I mean, it's very easy to calculate because you go on a computer and you just evaluate the error function in B, the error function in A, and then you get the result. So in view of practical applications, which in your case means exercises, if you need to evaluate a probability like this, where it seems that you have to sum over, I don't know, thousands or hundreds of values of the binomial, you may resort to this approximation and just calculate the error function into two numbers, then subtract them, and you're done. Okay? Okay, I just want to make one more comment on this result, the integral theorem, or I think Laplace theorem usually. Oh, can I cancel this? Okay. Okay, if you remember from the beginning, we started with Sn x1 plus x2 plus xn. Right? And basically we add that x1 can be 0, can be 1, the probability that x1 is 1 is equal to p, but it's just old for, I don't know, let me say I. Okay, this is true for all I, where I goes from 1 to n small n. And then you have the probability that xi equal to 0 is equal to q, which essentially is 1 minus p. Okay, now you should be able to calculate the mean of these variables. Right? This is easy because it's the probability that x1 is equal to 1 times 1 plus the probability that x1 is equal to 0 times 0. So at the end you just get p. Okay? And if you try to calculate the variance, this is again a very simple exercise, you will get p times q. Try to do this. It's very simple. These are very basic calculations of probability. So if we rewrite that expression, see, we get that the probability that, okay, here we have a Sn minus n times p. I'm writing p as, okay, I'm omitting a because it's equal for all the indexes. Then now you can write it as the square root of n times the square root of the variance of x, right? This is approximately equal from AB, the x. Okay. So now we have just proved, well, kind of proved this result for x, which have this very simple distribution. Just can be two values, 1 or 0, with this probability, and you have this very nice result. But I think that in the next lectures, we will see that this result is much more general. And indeed, this holds for x, whatever is their distribution. You just need to have n different random variables, which are identically distributed. You see the distribution is the same for all the x. They're independent. Okay, maybe I just went over this, but they are independent, right? And you will get this nice result. We've essentially proved it for x with this distribution, but it holds true if you have n identically distributed and independent variable, but no matter which the distribution is. This is called the central limit theorem, and is one of the most important theorems, and maybe the most one in probability. I think that you will see it in the next lectures, but just to give you a flavor that in some sense today we have proved it in a very specialized case for x with this distribution, but this is true in the most general case. Okay? Okay. So I hope it's clear. Okay, quick recap. We started from the binomial distribution, which tells you the probability of having k successes out of n trials. Of course, the trials need to be identically distributed and independent, like this. We've approximated this probability, the probability that Sn is exactly equal to k with this expression. And this is the local theorem, the Moivre-Laplace theorem, I think. Then we saw how we can write it in a different way, the integral theorem, which is the probability that this quantity, which is a normalized quantity, is in this interval. then it's just the integral extended to this interval of the normal distribution, right? The Gaussian with a 0 mean and 1 variance, and I would link this result to the central theorem limit of yes. Okay, now we'll see a different limit for the binomial distribution. I think I need to go a bit. Okay, this is easier, so and not as long. Can I? Okay. Unfortunately, I think we will have no time to make examples today, but we will do some examples in the tutorial, and not in the next one, maybe in the other one, because Antonio told me that I need to just do the exercises of your test and then some basic exercises on probability. So this will be for tomorrow. I also send you an email. Have you received it? Okay, try to make that exercises. Maybe they're very easy, maybe they're not, just to get an idea of your understanding of probability, and we can try to do them tomorrow, okay, in the tutorial of tomorrow. Okay, so let's forget for a moment about these approximation, and let's go back to our exact binomial distribution. Okay. Okay. Okay, so now suppose that P does depend on n. So P is now a function of n. Now, okay, maybe it will be a little difficult to accept for the moment, but I will try to make some examples. Let me just prove the theorem before, and then if we have time, we'll discuss it, or otherwise we'll discuss it in the tutorial. So the thing is that now P depends on n, and in particular, it goes to 0 with n going to infinity. I know this may seem a little bit counterintuitive because you're saying, okay, but I'm doing more and more trials and the probability goes to 0. How can this be? But just with the patience. But the important thing is that Pn times n, this quantity stays finite. So the limit, this is finite, like lambda. So if you remember, the mean of this distribution is exactly NP, right? So this means that the mean stays finite. Okay? So if P does not depend on n, you expect the mean to increase linearly with n. It's n times P. P is a number, and then it's increasing linearly with P. And this is the previous case. Now it's a bit different. P depends on n, so that n times P stay finite. So the mean stays finite. Okay? Again, be patient. We will discuss that later. Okay, so what does this mean? That P n, has to go like 1 over n plus lambda over n actually, plus, okay, other orders like something 1 over n squared and other things, so that when you do the limit, you get lambda. Okay? So this is the case we're discussing. P, it's going like lambda over n. This limit is finite, but P, when n approaches infinity, goes to 0. In this way. Okay. So keep in mind this result. And again, this is, let me write down it explicitly. Okay. So let me focus on this factorial. This is n times n minus 1. Then at some point you have n minus k minus 1, right? Then n minus k, then n minus k plus 1, and so on, up to 1. Okay? And here you have k factorial, then you have n minus k, n minus k plus 1, and so on up to 1. Then you have p, k, q, minus 1. Right? So you see that this just simplify this part, and you end up with n minus 1 times n minus k minus 1 divided by k factorial. Now, just rewrite all these terms in this way. N, then you put this n out, you have 1 minus 1 over n, right? Do the same thing here, and okay, the next term will be like this, with an n, and then again you have an n, 1 minus k minus 1 over n, right? This is divided by k factorial, and here you have pi k, q, and minus k. Okay? Okay, so at the end, let me just write down here so you can remember this. This is approximately equal to lambda over n. Okay, this is all true in the large n limit. So, okay, at the end you can count this n, 1, 2, k minus 1. So you have k minus 1 n plus this one, you have k n. So n to the power of k times 1 minus 1 over n, 1 minus 2 over n, what? 1 minus k minus 1 over n. Okay, here we have k factorial, and what else? Oh, and now let me replace p with that expression, lambda over n. Lambda over n to the k, and 1 minus lambda over n to the n minus k. Okay? Is it clear? So now I'll just rearrange the terms a little bit. 1 minus 1 over n, blah, blah, blah. 1 minus k minus over n. And then you see this n to the k just cancels out with this one. You end up with lambda to the k, k factorial, and 1 minus lambda over n to the n. And then again, 1 minus lambda over n to the minus k. Okay? So now we'll take the large n limit. Can I, that part? Is this okay? we're almost done. Okay, let me see what happens. Now we make the large n limit. Okay, what's happening? Oh, you see that all these factors are going to 1 because this one is going to 0, so you have 1. This is true even here because k, it's fixed even when n goes to infinity, so this will be 1. And even here, you see, this will be again 1 to the minus k, which is 1. So these are 1. Then you have this one, lambda k to the minus k, to the k factor, and then you have this thing. But if you can just recall, let me a very well-known result. If you do the limit of n to the infinity of 1 minus lambda n over n, this is equal to e to the minus lambda. This is calculus. I don't know. It's the limit of this succession of numbers. Maybe if you place lambda equal to 1, you see that you exactly recall the Nepero number. So I don't know if you know this result, but you can find it, I think, on all basic calculus books. So it's just the limit of this succession. If you do the limit, you get e to the minus lambda. Maybe you know the definition of E, Nepero number. If you put lambda equal to 1, you exactly recall it. But there's a more general result, which is this one. Okay? So you end up with this very, very simple, very neat result. So now the probability that Sn equals to k, this limit, which is not simply a large n limit, but remember you have that the mean, so the n times p stays finite. When n goes to infinity, you get this result. Okay, so let me say probability that Sk is equal to k, Sn is equal to k. And this is the Poisson distribution. Okay, maybe you have not seen it yet. The Poisson distribution has just one parameter, which is lambda, which is also the mean of the distribution. And the only variable is k. So you can calculate it now for integer numbers. So k stays equal to 0, 1, 2, 3, okay? The Poisson distribution actually is defined for k positive, so it's not bounded by n. So again, this is a limit of the approximation because you know that the binomial distribution it's only defined up to n, so you do not expect to work for very large values of k, especially for k larger than n, okay? But still, this is a very interesting, very simple approximation. And okay, I don't know if I have time to give you an idea of what this limit means, but it's like just make you a very simple example. Now, suppose that you know that at I don't know, phone switchboard will arrive 10 phone calls per day. Okay, so then you have 1 day, and you know that, okay, on average you will have 10 phone calls per day. Okay. Now you can just divide this interval, which is 1 day, in 2 parts, and okay, you know that you will get maybe on average 5 phone calls in half day and 2.5, okay, and you just continue this procedure, right? Just continue to divide, to divide, to divide, right? So at the end, you have that. If you think at the probability of having one phone call at one small interval, which is p over n. Okay, at some point this number will become less than 1, and you can interpret it as a probability. Okay, you're doing just dividing. You start from 1 day, then half a day, then maybe you arrive at an hour, at a minute, at a second. This number will become smaller, and at some point you will interpret it as the probability to get a phone call in that small time interval. So this probability times n, the numbers of the interval, stays constant, because you know that at the end of the day you'll get on average 10 phone calls, right? So now if I ask you, okay, which is the probability of having k phone call at the end of the day, you can just use the Poisson. You just evaluate lambda, which is 10 phone calls per day, and just you put k inside and you get the result. So this is a kind of example when the mean is fixed, right? But then as you increase the number of intervals, and the probability is just dropping down, okay? It's approaching 0. But at the end, the mean is constant. Okay? I just made you this very quick example. Maybe we'll get back to this and see in details how this approximation works. We'll try to do this with binomials, and then with Poisson, and I will try to convince you, I mean, in a better way than this is true, as well, just to give you a flavor, I mean, what this limit really means. The number of phone calls at the end of the day, it's not increasing linearly, it's constant, because you know that it's constant in some way. Okay? This is a starting point in a sense. You know in your problem that you have a fixed number of average calls, and it's and if you keep just making this interval smaller, this is just Pn over n, and the limit is fixed is lambda. It's 10 phone calls per day. Okay?